All right, so in this video, we'll look at a few examples of taking two-sided limits at least. Or, well, actually, there are a couple one-sided limits and a couple limits going to infinity. But yeah, we'll look at some examples of the sort of special limits that we defined as like definition 20.3. So the first sort of, and these are mostly just from the book, although there's one that I'm gonna skip. But so basically the most straightforward instance of this is like, okay, this is what they call example one. Is a situation where you just take the two-sided limit of a function that's just continuous at the point. So something like limit as x approaches 4 of x cubed is 64 because f is continuous at 4, and well, we can say the domain of f is just R, So the fact that the domain of f is R, the only thing that's like relevant about this is just that this means that we can find like an open interval around the number 4 where f is defined, right? And then the fact that f is continuous there means that any sequence approaching 4 will have f of xn approaching 64, right? So, I mean, we haven't actually formally proven any theorems about how, how continuity implies the existence of the two-sided limit. We haven't really stated that as a theorem, but it's pretty straightforward. So, yeah. So, yeah, we can say, yeah, they also, in this example, they include, like limit as x approaches 0 from above of 1 over x is plus infinity, the limit as x approaches 0 from below of 1 over x is negative infinity. They state these without proof here. We're going to do some similar ones in a later example, so with proof. So I'm just going to go ahead and state these without proof. But what we can say about this is this means that the limit as x approaches 0 of 1 over x does not exist, which is hopefully a familiar fact for all of you, that if the behavior of the function on the two sides of your limiting value is just different, then we simply say the limit doesn't exist, right? Even if there is a consistent limit as you approach from one side or the other. So those are some kind of simple examples. So let's just go ahead and move on to the next one. So example 2 here is taking the limit as x approaches 2 of x squared minus 4 over x minus 2. And so this is kind of an interesting one because this is and you've probably seen something like this before too, especially because, I mean, when you learn to calculate, derivatives, this is something that you might calculate as taking the derivative of the function x squared minus 4 at x equals 2. So if we let's call this expression g of x. Okay, so this function g of x is the function defined by this expression with the natural domain, right, that comes with that. So the domain of g is R without the point 2, right? Because the denominator here becomes 0, okay? Even though the limit, what we'll find out is that the limit actually exists, okay? So this is a removable discontinuity, basically. So G, or not a removable discontinuity, but G has, well, G could be extended, basically. So G is not defined at x equals 2, but can be continuously extended to take a value there. This is because for all x in the domain of G, we have G of X equals X plus 2, right? If you just factor this using the difference of squares and then cancel the X minus 2, when X is not equal to 2, you're allowed to do that, and then you end up with X plus 2. So basically, G of X, also in the language of restrictions, you could think of G is the restriction of f of X equals X plus 2 to R. So it has a deleted point, basically. There's a point that's been deleted from the domain. Okay, so anyway, long story short, this limit exists because basically, actually, you can argue if you take for granted that continuous functions have limits at points, then the fact that G can be extended continuously means that this limit exists and it equals the value of the extension. So the limit as x approaches 2 of x squared minus 4 over x minus 2. Actually, let's call this, instead of f, let's call it g tilde, just to be consistent with the notation. So this is g tilde of 2, which is 4. Okay? So yeah, it might seem very, technical, I guess, or sort of, yeah, it might seem like splitting hairs to say that this function is actually distinct from the function x plus 2. But subtle, or sensitivity to these nuances is critical going forward, especially when we get to the point where we want to define derivatives, because like I was saying, this divided difference expression pops up when you define derivatives. I mean, this is the definition of the derivative of G, or the derivative of x squared minus 4, sorry, at x equals 2. And so if you want to deal with that in sort of generality, you have to respect the fact that this expression is not defined when x equals whatever the constant term down here is, right? So this is really the language of like how we analyze limits like this. Okay. All right, let's skip ahead to example 4. So in this one, they look at 1 over x minus 2 cubed. So then they say, so limit as x goes to negative infinity of f of x equals the limit as x goes to positive infinity of f of x equals 0. And the limit as x approaches 2 from above of f of x is positive infinity, and the limit as x approaches 2 from below of f of x is negative infinity. Okay, so let's prove a couple of these. Okay, I'm going to prove the as x approaches positive infinity. Okay, so 1, and then also let's look at okay, let's say our second, the other one we'll prove rigorously is this one about approaching 2 from below. Okay, so for the first one, what we can say is so let's say right, well, let's think about the definition, right? What is the definition of saying that the limit as x approaches infinity of f of x is 0, right? That means we just need for there to exist some interval. So I want to show there exists an interval, c infinity, such that for all sequences, xn going to infinity in c infinity, we have f of xn going to 0, right? So the only problem is like we can't really let c be less than 2, because 2 is a pole, so we wouldn't want, I mean, well, for one, basically f is not defined. F literally wouldn't be defined on the entire interval if c was less than 2. But if c is equal to 2 or anything bigger than 2, so so we can take c equals 2, for example, because as long as c equals 2, then if xn is in this open interval, all the xn's are bigger than 2, so f is defined. Well, f is defined on this entire open interval. Okay, f is defined on to infinity. Let xn go to infinity be a sequence with xn greater than 2 for all n. Okay, then clearly by, well, they actually give the numbers. I'm just going to say section 9 theorems. We have xn minus 2 cubed approaches infinity, right? Xn minus 2 obviously approaches infinity, so xn minus 2 cubed approaches infinity. So again, by section 9 theorems, 1 over xn minus 2 cubed approaches 0, right? So that kind of finishes that one. Let's finish this off. So for 2, we were trying to show that as x approaches 2 from below, f of x approaches negative infinity. So let's say, okay, yeah. So for the second one, we just have to show that, well, some interval like less than 2, but like with 2 as an endpoint. So some interval like, well, really we can use negative infinity to 2. So, well, yeah. So we can take s is negative infinity to 2 and let xn be a sequence in S with xn approaching 2. Okay? Then we just have to show that the limit of f of xn is negative infinity. So I want to show the limit of f of xn is negative infinity. Okay? So to do that, all we have to do is, so first of all, so clearly, right, 2 minus xn cubed is greater than 0, right, for all n, since 2 minus xn is greater than 0. So, and 2 minus xn approaches 0, so 2 minus xn cubed approaches 0, right? So by the same section 9 theorem, so it was, I think theorem 9.10. So theorem 9.10, I think, is the one that says that if you have a positive sequence approaching 0, then 1 over that sequence approaches infinity. So by theorem 9.10, 1 over 2 minus xn cubed approaches infinity. And then it's, I think they cite an exercise for this, but it is simple to show that because 1 over f of xn, or sorry, not 1 over f of xn, because f of xn equals negative of this 1 over 2 minus xn cubed, this means f of xn goes to negative infinity. Okay? So anyway, all this to say that, this is how you would apply the definitions of these special limits here. I hope you guys sort of understand how this works with like the intervals and stuff for the two-sided limits. you're interested in finding an interval on both sides with a deleted point in the middle. And then for one-sided limits, you just have to find an interval touching that point on one side. And it doesn't matter how big it is. So if you can take it, like for some functions, you wouldn't be allowed to take negative infinity up to this thing. It's just that for this function, we can because, f is defined on this entire interval, and it's never, there are no like places where it diverges or anything. So it's not an issue. But we are free to take a smaller interval if we want, and then let xn be a sequence in that interval. It doesn't matter. Okay. So anyway, I think that's it for these examples. Yeah, and then in the next one, we'll prove some basic theorems about, adding and dividing and multiplying and so on, and how they affect limits.